All right, so um, we're gonna begin the summer session with uh, about about 3 weeks of heat and thermodynamics. We're gonna go through. If you have a copy of the textbook, which you do not need, it's not required. It's the same textbook that the Physics 1500 course is based on, and the chapter numbering from that book is what we're still using here. So, chapters 10, 11, and 12 within that book are the ones based on heat and thermodynamics. Chapter 10 is specifically going to focus on temperature and a few different properties of matter that are affected directly by temperature. Now, before beginning the conversation of temperature itself, it's important to keep in mind thermal energy. Even we'll go more into detail of some of the math behind thermal energy in the coming weeks. This week we're mostly going to focus on temperature, but you can't not bring up thermal energy when talking about temperature. So, to begin with, all forms of energy, well, there's lots of different forms of energy, and that energy can occupy lots of different objects. In previous physics classes, like in Physics 1500, mostly would have been studying mechanical forms of energy. There was units on kinetic energy, gravitational potential energy, and elastic potential energy. We consider all of these forms of mechanical energy because they are in a form that is readily available to just perform mechanical work. For example, these are the forms that your muscles tend to use most often. There's gravitational potential, elastic potential, but also some chemical potential energy in your arms that tends to be converted into kinetic energy as you move your arms around and as you transfer that energy into objects you're doing work on. So this thermal energy is going to be our first form of non-mechanical energy. Now, thermal energy is everywhere. It's probably come up in previous classes, even if you haven't necessarily done a heat and thermal unit yet. Thermal energy is just another form that energy can occupy. It's basically the energy of heat. And as an energy form, you can never detect any form of energy at all except when an object has that energy and when it does something with it. For example, you can't see kinetic energy, you just see that an object that has kinetic energy is moving. Like with thermal energy, if you look at something, you technically can't detect how much thermal energy it has. You can touch it and get a feeling for what its temperature is. You might see it glowing if it's really, really hot, but technically speaking, you're not seeing thermal energy when you're looking at it. You can only ever see what something does with that thermal energy. And most of the time for humans, you'll only ever really interact with that thermal energy when you touch something and, see how it feels. But like all the other forms of energy, thermal energy can transform, it can change what state it's in, and it can change what object has it. And the fact that it's able to move between different objects is the basis for temperature. And I'll elaborate more on that in a minute. As for what thermal energy does to an object, because every different form of energy causes a slightly different thing to happen in the object that has it. Kinetic energy makes things move, for example. When an object has thermal energy, this manifests most commonly as random movement of that object's subatomic particles. The warmer something is, the more thermal energy it has, the more energy its atoms literally have. And as a result of that, those atoms tend to bounce around a lot more. They're moving around more quickly, they're more energized, so they're bouncing apart and physically moving further apart than they normally would. The inverse of this is when an object has less thermal energy, and then its subatomic particles are less active. They don't have as much energy, they aren't moving around as much, so they don't bounce around as much, and they tend to drift closer together as a result of that. This is kind of like if you had a bunch of ping pong balls in a room, and normally the ping pong balls would all rest together, but if you turned on a fan in the room, suddenly now all the ping pong balls have a lot more energy, and they're going to start bouncing around, bouncing off of each other, and they'll take up more space as a result of that. If all the ping pong balls would fit in a normal box, as soon as you start adding energy to them, they're going to scatter all over the place and take up more overall volume than the box they were originally in. Atoms with thermal energy do the same thing. And one of the easiest ways to kind of feel this happening is in turning some energy into thermal energy. And an example I've used for this in the past, this is an example that I use starting in Physics 1500 when talking about friction. If you just take your hands, put your palms together, and just start rubbing them across one another, that action makes your palms feel warmer. Your palms start to warm up. And that's because the friction between your palms takes some of the kinetic energy, takes some of the work that you're doing, and takes that energy away from motion, because the friction slows your hands down. If there wasn't friction, your hands could slide faster, but since there is friction, they move slower because it takes energy out of the motion and turns it into thermal energy, which is now in your palms. And you can feel your palms warming up as those atoms absorb that thermal energy. And as the atoms in your hands get warmer, they get more energized, they start moving around more. And this is what can lead to burns in people. I'm not quite a biologist, so I don't necessarily know all of the cellular facts about what happens to a burnt skin cell. But if you added enough heat to a skin cell, eventually the cell materials would start dying, the water inside the cells would start boiling because it has more energy and it's moving around more, and that can cause damage. That's really uncomfortable, and it's all due to the increased random motion of the particles. So we have evidence that this is what matter does when it possesses thermal energy. Objects with more thermal energy have more random movement of their particles. Objects with less thermal energy have less random movement in their particles. And this is ultimately what temperature, the math behind measuring temperature, is trying to measure and quantify. If there's any questions or any want for me to elaborate on something at any time, please do let me know. Kind of already made this point. The faster the atoms go, the more collisions there are. So in a colder object, there's less energy, therefore there's less collisions, and the particles tend to be closer together. In a warmer object, there's more thermal energy. The objects are bouncing off of each other very chaotically, and they tend to drift further apart as a result of that. We're going to get into that within this particular chapter when we start talking about thermal expansion, the idea that warmer things, their particles drift further apart, and therefore warming something up actually does make it bigger. For a simple example of that, just to illustrate to this picture, steam takes up more space than ice. In an ice block, all the particles are rigid and locked together in a specific fixed volume, but if you were to melt that ice and turn it into steam, that steam billows out and takes up more room because its particles are further apart because it is warmer. Those particles bounce off of each other more and take up more space. We'll look at the math for that phenomena later. But things to note right now: thermal energy can transfer between different objects. Objects that have more thermal energy, their particles are moving around more chaotically, more frequently, they're colliding more, and they end up drifting further apart. That process reverses when the object has less thermal energy. And the primary means through which humans try to detect thermal energy is, I stumble over my words sometime. One sec. sorry. Sorry about that. Yeah, I mostly mentioned everything on this slide already. Peony, what are you doing? Puppy gets a little noisy sometimes, sorry. Okay. So, like with all forms of energy, thermal energy can transfer between different objects that possess it. And the method by which thermal energy transfers that we're most going to be talking about is conduction, because that's largely the method that humans most directly experience hot and cold through. The concept of conduction is just two objects are directly touching and thermal energy can flow from one object to the other through that thermal contact. Say, for instance, you touch something that's really, really hot. Since the object you're... I need a demonstration. This is a candle. And if it was lit and if it was warm, it would have more thermal energy on average than my hand. And so if my hand was to touch that warm object, suddenly now the particles of my hand are colliding with the particles of the candle. We call that thermal contact whenever two objects are in a state that energy can be exchanged between them. And since my particles are now colliding with the candle's particles, the hotter particles of the candle are going to collide with my hand. Those hot ones will hit my colder particles and exchange energy from one to the other. This works like all of the collisions that you've studied and talked about in Physics 1500. Say when there was a momentum example when a car would hit another car and then there'd be an energy exchange and they might bounce off of one another. Subatomic particles work exactly the same way. All your atoms are basically ping pong balls. And so, when the hot particles of the candle touch the colder particles of my hand, there's going to be an exchange of energy in that collision. The hotter particles will lose some energy as they hit and give energy to the colder particles of my hand. So that means that thermal energy ends up transferring out of the candle and into my hand. So anytime you've ever touched anything and it's felt hot, that was the physical sensation of thermal energy leaving whatever you're touching and entering your skin. The sensation of hot is the way that your nerve endings interpret thermal energy entering your body. The inverse of that is when you feel cold, and coldness is what happens when thermal energy exits your body. Say instead of a candle, I was touching my ice water. Ice is colder than me, so if I was to touch the ice, then my warmer particles would now be colliding with the colder particles of the ice, so energy would transfer out of my warmer hand and into the water. So the sensation of hot is your body gaining thermal energy. The sensation of cold is your body losing thermal energy. And the human body most often detects this through the act of conduction. You simply just touch something, and there's going to be a thermal energy exchange based on the difference in temperature between you and the object. Any two things that touch can conduct thermal energy. Right now, in my cup of water, there's very cold ice touching less cold water, so the ice warms up as the water cools down, and then all of it's touching the warmer air above it, so thermal energy transfers out of the air and into the ice, and that's why it slowly melts. So, any direct contact between any two objects can result in conduction. There's two other methods, methods of heat transfer, which will come up from time to time, so it's important to classify them. Pardon me. Excuse me, sorry. Those other two methods are convection, which is basically conduction with extra steps, and radiation. Convection is what happens inside of an oven and also in boiling water. If you put a cold turkey in your oven to cook it, the hot part of the oven is usually the heating coils on the bottom of the oven. It'll vary a bit depending on the construction, but at least in most electric stoves, and even in most gas stoves, electric ovens and gas ovens, there's some element at the bottom that becomes very hot, and that thermal energy is what cooks whatever's in the oven. But when you put the turkey in the oven, the turkey is not actually touching the hot element on the bottom. Let's see if I can actually create a quick visual. Hold on. Whoops. Trying something new with Google Meet. It doesn't seem to be working. Okay, I will figure out how that technology works later. Okay, very quick, very terrible drawing. Physicists aren't artists most of the time. You have a turkey, poorly drawn turkey, in your poorly drawn oven, and it is not touching the heating coils on the bottom. Since they're not actually touching, there's no thermal conduction between the two. So how does the heat get from the coil into the turkey? The answer is convection, and it lies in the fact that even if the turkey isn't touching the heating coil, there's still air between those two things. Air's everywhere on Earth's surface. It's pretty good for us. It works out pretty nicely. And in this particular case, what happens is the turkey's not touching the coils, but the air inside the oven is. So the coils warm up the air surrounding them, and that warm air is going to rise up and touch the turkey. You've probably heard the adage that hot air rises, cold air sinks. If you're unfamiliar with that fact, it is true. Whenever air is warmer, it tends to float upwards through colder air to try to reach a higher elevation. And this does tie back to the idea that objects with thermal energy, more thermal energy, objects that have more thermal energy, particles move around more, they drift further apart, so hot air is less dense than cold air. And you float when you're less dense than the fluid you're surrounded in. So hot air literally floats to the top of the oven because it's less dense than the cold air that's everywhere else in the oven. This is also the phenomena that creates most weather on Earth. A combination of hot air rising and cold air sinking creates most weather phenomena on this planet, to my knowledge. So within this particular oven, hot air from the coils rises up to the turkey. Once that hot air touches the turkey, heat can conduct from the air into the turkey, so now the turkey is warmer. It did get thermal energy, it just needed to use the air as a go-between. Once that air touches the turkey, now that air is cold again. And hot air rises, cold air sinks. So the cold air sinks back down to the coils in order to heat up. This constant cycle of hot air rising and cold air sinking is called a convection current. You might have heard that term before in relationship to a convection oven. And that's the secret to how all food gets cooked in an oven. And this is also why, if you've ever opened the door to an oven that is turned on, you sometimes feel a blast of hot air escaping the oven coming up towards your face. This is likely more apparent if you wear glasses, because that blast of hot air carries steam with it that tends to immediately condense on your glasses. So, hot air rises. That's the reason that ovens work, and we call that process convection. Convection requires the two objects in question, the heating coils and the turkey, not be touching directly, but there has to be some fluid between them that will allow the heat to travel and that will allow the convection current to form. It doesn't actually have to be air, it can be any fluid. And if you're unfamiliar with that term used scientifically, fluids can refer to either gases or liquids, because both of those states of matter exhibit fluid tendencies. Liquids and gases can both pour, they can both flow, and that's what is important for forming a convection current. So you can also form convection currents in, say, a pot of boiling water, and that's how you tend to cook things when you boil them. You put a pot of water on top of the stove, heat from the heating element heats the pan, heats the water on the bottom, the hot water rises, cold water sinks, and you form that convection current that constantly heats up and stirs around your pasta or what have you. So, convection is basically conduction with extra steps. It requires a fluid medium, and it requires that the heat travel upwards. Convection cannot heat downwards because the hot air rises and the cold air sinks. So this is one reason why if you've been to a bonfire lately, the hottest place to be is standing directly over the fire because air warmed by the fire rises upwards. If you were somehow standing under the fire, you wouldn't actually feel any all that hot because all the heat rises, and if you were somehow standing under it, you'd be fine. So convection requires a fluid medium, and it can only transfer heat up. The last method is radiation, and this is the method through which the sun warms the Earth. If you think about the distance between the Earth and the sun and the fact that the vacuum of space is empty, the sun is not touching the Earth, so the sun does not warm the Earth via conduction. There is also not a fluid medium in the vacuum of space for convection to occur. Space is empty, so there's no way for a convection current to form between the Earth and the sun. So instead, the Earth is warmed by the sun through radiation. And the concept of radiation is just simply the act of energy traveling from one point to another as a photon, as a wave of electromagnetic radiation. Light is the most common, or at least light is the form of electromagnetic radiation that humans are capable of detecting. Your eyes are designed to detect light. It is a form of electromagnetic radiation. And light's primary purpose is to carry energy from point A to point B. Anytime you've seen something, what you're seeing is the light traveling from that object to your eye. In the case of the sun radiating towards the Earth, light from the sun radiates energy constantly. That light travels to the Earth, and eventually it's going to hit something on the Earth, like the atmosphere, like the surface, or like your skin if you're outside on a summer day. And whenever light hits anything, since light is basically traveling energy, when light hits you, you absorb some of that energy. And most commonly, that energy is absorbed in the form of thermal energy. And this is why, when you're in direct sunlight, you tend to be warmer than when you're not in direct sunlight. Literally, light warms you up by virtue of the light hitting you and its energy being absorbed into your cells. That light is constantly warming the entire planet. So, most of Earth's energy that we get from the sun is in the form of radiation. And this is also the same principle that lets solar panels work. Solar panels are machines specifically designed to absorb energy from the sun and turn it into electrical energy rather than just thermal energy. So, same basic process, just a slightly different application. And so these are the three different methods through which thermal energy can transfer between two separate objects. We're mostly going to focus on conduction, but the other two are important because of how they affect life on planet Earth, and they will come up from time to time in our discussions. Let me know if you guys have any specific questions as we're going through this, or if there's anything you want me to readdress. So, thermal energy can move between two separate objects, can go from point A to point B, and thermal energy always flows from hot to cold. The presence of thermal energy is what makes something warm. The absence of thermal energy is what makes something cold. As a result, thermal energy always flows from hot to cold because it's going from a state where there's a lot of energy to a place where there is less energy. It's like the flow of water. Water always flows from high concentration, where you've got a lot of water, like, say, a lake, to areas of low concentration. Water flows out of a lake where there's a lot of water into smaller rivers where there's less water. So, like a lot of things in biology and chemistry, thermal energy goes from high concentration to low concentration, from hot to cold. Coldness technically doesn't really exist. Coldness is the absence of thermal energy. It's not that you have absorbed coldness into yourself, it's that you've lost thermal energy when you feel cold. So, thermal energy always flows from hot to cold. And thermal energy will just automatically do this whenever two objects are touching or interacting until their temperatures equalize, until the concentration of energy on one side and the other normalize and equalize out. The image shown here, for example, say we have a hot object touching a cold object and heat is able to flow between them. Let's say one of those objects is 0 degrees Celsius, the other is 100 degrees Celsius. When they touch, when they are allowed to touch, thermal energy is going to transfer from the hot object into the cold one. And this process will continue until their temperatures equalize. As long as one of them is hotter than the other, there will always be a net flow of energy from the hot one to the cold one. But once they're the same temperature, now the concentration is even across both sides. And if they're still touching, it means that the particles in one and the particles in the other are bringing the same amount of energy into the collisions between the two objects' different sets of atoms. As a result, whenever two things that are the same temperature touch, there is still technically an exchange of energy because the particles are still colliding and bouncing off of one another, but it means that each side doesn't really gain or gain. No side gains any more or less than it loses. When two things that are the same temperature touch, the net energy flow between the two is zero. So whenever you touch something and it does not feel hot or cold, that means it's at the same temperature as you, and there's no net energy flow for your nerve endings to detect. We'll talk more about the laws of thermodynamics later. And I want to make sure that we talk about temperature today so that we can use that as a starting point for other formulas that will come up, and so that you can begin looking at the homework questions that involve temperature conversions. So, we've done a lot of talk about thermal energy as a whole today, and we kind of have to start with talking about thermal energy because thermal energy goes on to inform everything else that we're talking about in these 3 weeks of heat and thermodynamics. But now we're going to shift gears and focus specifically on temperature, because temperature is one of the first and easiest ways that humans are able to get a rough estimate of how much thermal energy an object has. Before humans were ever measuring thermal energy itself, we were measuring temperature. And as that primary unit through which we determine how much thermal energy something has, roughly speaking, temperature is very important, and it comes up in a lot of our formulas, and it's important to understand what it actually means. Temperature is not an absolute measurement of how much thermal energy a specific object possesses. It's designed as an average measurement of the energy of that object's particles. So say, well, let's just examine the ice in my ice water. If I was to take a block of this ice, a cube of this ice, excuse me, this ice is currently at 0 degrees Celsius, 32 Fahrenheit. And that piece of ice, its particles have some amount of energy inside of it. And each of those individual particles, if you were to rip one of those water molecules out of that ice block and just study it, theoretically you could determine how much energy that one molecule had. And temperature is that measurement. It is a measurement of the energy level of a one random particle of that particular object. And since we know that my ice is at 0 degrees Celsius, if you've ripped out one of its 0 degrees Celsius atoms and compared it to an atom randomly ripped out of a different piece of ice at 0 degrees Celsius, they would both have the same energy level because they're both at the same temperature. Temperature is a measurement of the average kinetic energy of the particles that make up an object. And since thermal energy causes random movement of subatomic particles, thermal energy is secretly a form of kinetic energy. Kinetic energy is the energy that makes objects with mass move, and subatomic particles have mass. So when they move, they must have kinetic energy. And so, some very smart people have taken the kinetic energy formula. This is the same formula from Physics 1500. Kinetic energy equals 1/2 times an object's mass times its velocity squared. Some very smart people took that formula and realized you could apply it to the energy level of subatomic particles. Because if they have energy based on what temperature they are, if something's temperature determines the energy level of its particles. So some very smart people took that original formula and converted it into this piece right here. The kinetic energy of a specific subatomic particle inside of an object is equal to 3/2 times K, which is this constant right here. You'll never have to memorize that. Anytime a lowercase k comes up in a formula, it will just be this number. And then times the object's temperature. The reason this formula exists is because subatomic particles are really, really hard to actually measure the mass of, and oftentimes impossible to measure the velocity of. So the old formula doesn't really work if you want to know the kinetic energy of a specific particle. Instead, we tend to base the energy level of atoms more on their current temperature, since that's a more easily measurable variable. And so that's what this formula exists as. It's meant to illustrate the connection between temperature and the kinetic energy, the thermal energy of subatomic particles. So, object's energy level determines its temperature. Temperature is just a measurement of that average. The device through which humans primarily measure temperature is called a thermometer, although thermometer technically refers to like the old-fashioned thermometer that has liquid in it that expands. Electric thermometers have devices called thermistors and thermocouples. If you've ever heard those terms before, they simply refer to electrical mechanical components that can detect temperature. And while I'm on this slide, I want to point out to you, since this affects your own perception of temperature, human bodies do not have built-in thermometers. If you touch something, there is no part of your nervous system, there is no part of your brain that is specifically designed to say, yes, this object I'm touching must be approximately 80 degrees Celsius. You don't have a mechanism for that. You cannot touch something and immediately just know a number for its temperature. What happens is, when you touch something, all your nervous system is able to detect is how fast thermal energy is entering you or exiting you. Touching something does not immediately tell a human being its temperature. What it tells a human being is how quickly thermal energy enters you if you're touching something hot, or exits you if you're touching something cold. For example, if I was to stick my finger into my ice water is pretty cold. And that means that it's at a noticeably lower temperature than me. Thermal energy will exit my body at an average speed, and my body will register that sensation, the feeling of thermal energy exiting me, as the sensation of cold. But there are colder things I can touch than ice. I could touch dry ice. I could be on an Antarctic expedition where temperatures get very far under 0 Celsius, under the freezing point. Those things are a lot colder than my ice water. And if I was to touch those, thermal energy would still exit me. You would detect that flow as the sensation of cold. But when the colder something is when you touch it, the faster thermal energy is going to exit you. And that higher rate of thermal energy transfer is what your body detects as a more extreme cold. Your body does not detect temperature. It detects the speed at which thermal energy enters or exits you. Touching something colder means that more energy exits you more quickly, and you interpret that as a sharper, more pronounced cold sensation. Same thing when you touch something that's very, very hot. So touching something that's very hot, more thermal energy enters you more quickly than if you touch something that's just lukewarm. And more thermal energy entering you more quickly results in a sharper, more intense sensation of hot. And all of those very sharp sensations tend to trigger our pain receptors, because I believe, not a biologist, so I'm not the best person to speak to this, I believe that your temperature receptors are very closely linked to your pain receptors. So when they get overwhelmed, you start detecting pain, and after a while, the pain from extreme cold and the pain from extreme heat feel the same, because your cells, it's the same mechanism detecting the pain and detecting the thermal energy flow. So, you don't have a thermometer, you detect heat flow, rate of heat flow through your skin. It's just something that's worth noting. Okay. I want to make sure we cover the different temperature scales today, since we're going to be using them for the entire duration of this month. So, there's 3 temperature scales. I'll go over them briefly. I talked more about their history in the pre-recorded version. The 3 temperature scales that exist are Fahrenheit, Celsius, and Kelvin. And depending on which science classes you've taken, you've probably used various different combinations of them at various different times in your life. Fahrenheit was invented first, and that's probably why Americans still use it, honestly. It was the first temperature scale ever invented. But science tends not to like it because its numbering feels kind of arbitrary. Freezing point's at 32, boiling point is at 212, and there's 180 degree separation between freezing and boiling. The man who invented the Fahrenheit scale, Gabriel Fahrenheit, It made sense to him at the time because of what he was researching and because of the way his notes worked, but a lot of the world has decided that it makes less sense than some of the other scales that were invented since then. Celsius is the scale that came next. It was likely invented within, the same 50-year span as the Fahrenheit scale. It was invented by a different scientist named Anders Celsius, and Celsius was invented because a lot of people were frustrated with Fahrenheit. Fahrenheit wasn't a very good scale for metric uses, and so Celsius was invented to become the new metric scale for temperature. It works in base 10, freezing's at 0, boiling's at 100. That system made the most sense to the people using it at the time, and so Celsius as a scale was adopted and used for unquestioned for about a century by the scientific community until the idea of absolute zero became popularized. If you're not familiar with the idea of absolute zero, I'll go over it briefly. If you think of a block of ice at 0 degrees Celsius, it's very cold, it's frozen solid, but it still has thermal energy inside of it. There exists temperatures colder than the freezing point of water. Doesn't happen a lot in South Carolina, but the weather can get below freezing. If freezing is 32 Fahrenheit, sometimes we do have days that gets down to 30 Fahrenheit, 28 Fahrenheit. And in the Celsius scale, that means that those colder than freezing temperatures are less than 0 Celsius. They go into the negatives. That means that 0 Celsius is not the absolute minimum thermal energy level an object can have. Which posed the question, what is the lowest thermal energy level something can have? What is the coldest something can be? That absolute coldest temperature is called absolute zero, and it's the point where you've removed all of the thermal energy from an object. If you've got a block of ice, you can keep taking thermal energy out of it until it hits absolute zero, and that's the point where it has no thermal energy left. Its particles have no energy to move. They are locked perfectly in place, frozen in time. It's very weird. It doesn't happen normally in nature. You will never encounter it in the world around you. The situations to create it are just impossible. But it is the coldest that can exist. And so when we realized that, we needed a new temperature scale that could reflect the fact that that new absolute zero is the coldest, and we needed that number to be 0 so that it would adequately reflect the thermal energy level of the object. 0 Celsius, you don't have 0 thermal energy. We needed a new scale that could better represent that. And that scale is the Kelvin scale, ultimately. Kelvin scale was invented specifically to take the place of Celsius and to represent the fact that 0 Kelvin was now the absolute coldest that could exist. 0 Kelvin is absolute zero, and every other temperature past that is just been adjusted from Celsius. 0 Celsius is negative 273 Kelvin. Sorry, reverse that. 0 Kelvin is negative 273 Celsius. Excuse me. The Celsius scale was literally just adjusted to create the Kelvin scale. And because Kelvin represents absolute zero best, it is now the temperature scale used most often in scientific settings, in the metric system. All three of these scales coexist. They all measure exactly the same thing. The difference between them is really just the same thing as the difference between meters and feet and miles. Measures the same thing. You just have to be able to convert back and forth between them. So to facilitate that, there are some conversion formulas. These formulas are on the class formula sheet on our Brightspace page. To look at them briefly, this formula here that I'm circling with my cursor is the conversion between Celsius and Fahrenheit. If you have a Celsius temperature, pop it here, multiply it by 9/5, add 32, and that gives you the Fahrenheit version. You can reverse that to convert Fahrenheit into Celsius. And subsequently, this is the conversion between Kelvin and Celsius. The Kelvin and Celsius scales are very similar. They were designed to be that way. So as a result, to convert Celsius into Kelvin, you just add 273. Or if you want to convert Kelvin into Celsius, you would subtract 273. This class is... all of the formulas for this class are designed to use Kelvin. Depending on how much chemistry you might have taken, you might have used Kelvin before, you probably used a lot of Celsius. This class will primarily be operating in Kelvin and Celsius. Fahrenheit will come up occasionally, since it's used by the American Weather System, but it'll mostly come up in the sense that it needs to then be converted into Celsius and Kelvin. So, as such, these notes have some quick sample questions designed to help facilitate using the conversion formulas. In a minute, the slideshow has my math in it if you want to look over it as you're using the formulas in, say, homework. For right now, for our purposes here, I don't want to lecture just at you too much today. So I want to show you the formulas and then give you some time to rest and then probably work on the homework outside of me talking at you. What I've got listed here is 45 in each temperature scale. 45 degrees Celsius, 45 degrees Fahrenheit, and 45 Kelvin. One interesting thing to note is that degrees Kelvin is not a thing. It's only degrees Fahrenheit, degrees Celsius, and just kelvins. I don't know why Kelvin did that when the scale was invented, but it's just the way it's said these days. You don't say degrees Celsius, you don't say degrees Kelvin. The unit is just kelvins. I'm going to show the conversions between these and other temperatures real quick. I just want you to quickly think about, are each of these hot or cold depending on your normal experience? Is 45 Celsius hot for a human being? Is 45 Fahrenheit hot for a human being? And is 45 Kelvin hot for a human being? So, I've got my work shown here on the sidebar. If you load up the notes that are saved to Brightspace, my work will be in there too. 45 Celsius is, and I go over this because a lot of Americans still don't have a very good internal metric for the conversions. 45 Celsius is pretty hot. It's pretty warm. 25 Celsius correlates to about 75 Fahrenheit. So 25 Celsius, 75 Fahrenheit is room temperature. That's the temperature most humans exist at. 45 Celsius then is pretty hot, 113 Fahrenheit. So that would be like desert temperatures. That would be like if you had a fever this high, you'd be in the hospital. So 45 Celsius is pretty warm. Correlates to 318 Kelvin. 45 Fahrenheit, if room temperature is about 75 Fahrenheit, 45 Fahrenheit's colder than average. Not quite freezing, but on the way there. This is probably a crisp fall evening. That correlates to 7.2 Celsius and 280 Kelvin. Meanwhile, 45 Kelvin, considering that 0 Kelvin is absolute zero, and water freezes at 273 Kelvin, 45 Kelvin is cold. It's very cold. It's almost absolute zero compared to what you normally experience You will never detect a temperature anywhere near as cold as 45 Kelvin. If you were exposed to 45 Kelvin, your body would be immediately turned into an ice sculpture. 45 Kelvin correlates to negative 228 Celsius and negative 248 Fahrenheit. I hope you never experience a temperature like that, because there's no coming back from it. This temperature does not natively exist in nature outside of very specific circumstances. So, that in terms of lecture is where I'd like to call it for today. I don't like to sit and talk at students for too long. I find that becomes unhelpful for learning. I'd like to know how you guys feel at this particular time. This is what I'd call the first main batch of content. I know there was a lot of talk about just what thermal energy is and does, and only just barely touching on the math. We're going to use the temperature conversions more in the coming couple of formulas. So what I'd recommend you guys do now, first of all, if you have any questions, I'd like to talk about them. So please let me know. But what I'd advise right now is we can pause here so that you're not just getting talked at for 2 hours. And what I recommend doing is taking a break, looking over the notes at your own speed, and beginning the homework. At this particular time, there's only but so many math questions in there that are worked from the formulas we've looked at today. But I want you to pause. We are going to pause here unless you have questions. If you have questions, please tell me. But otherwise, I say we're going to pause here. You guys can drop out of the call, look over the homework. If you haven't accessed WebAssign yet, if you have not looked at the homework yet, I ask you to do so now, so that you can have that begun. I find that beginning something makes it easier to return to it. And just look over it, see which of the questions you have the information, the formulas to work at the time being, and I'll still be here if for you to drop back in and ask questions about things. So, how you guys feel right now? All right. Cool. So, yeah, the standard lecture time for these summer classes is 2 hours a day. And I don't want to just talk at you for all 2 of those hours. I find that not good for human attention spans. So we'll pause here. You guys can hop out of the call, take a break, look over the homework, and if you have questions before noon, drop back in and I'll still be here. Cool? Alrighty. Let me guys know what you need. Take a quick break and have a good one if I don't see you again.